the sampling interval. Here we are only talking about what information is needed from the application layer to the link layer and what information is needed from the link layer to the application layer and how to use this. So we are using a maximum problem in the link layer and a minimum problem in the application layer. This is how we are formulating the problem. Okay? Any questions here? And the way we are implementing it is by finding the back-off interval so that if somebody has a lot of data, he would transmit first. So that means in order for him to transmit, he should have more data to transmit. That's what it boils down to. So let's say that in what is the analogy in the network, like in a highway. So let's say that you have an entry point. At the entry point, there are a lot of cars backed up. They are the first ones to get access to the highway. You see what I'm trying to say? Why? Because there are a lot of cars waiting for a long time. You see? So think about a highway where you have multiple entry points, and one of the entries, let's say there is a Kumbh Mela or whatever festival happening, there are a lot of cars waiting to get onto the highway, whereas in the other entry points, there are not that many cars, right? Because if there is a backup, that means in that particular entry, people are waiting for a long time. That's the delay will increase. So you give preference to those guys coming in. So that is what we are trying to do. We are maximizing those that really need to transmit. And that's how it's incorporated. How is this incorporated as part of the back-off interval? So that means that particular subsystem would have a smallest back-off interval. So it's going to go first onto the network and then it's going to transmit. You see, that's a very simple idea. But when there is a collision, that means someone else tries to sense the network, there will be a collision. Then both will back off, but the one that is going to back off smallest is the one that's going to transmit because you want to reduce the amount of delay. You understand that? So the delay is proportional to the back-off interval. The longer you back off, the longer is the delay. You understand that? Longer is the delay. Right? Because he's backed off. He's not able to get onto the highway. Okay? So longer is the delay. So that's how we basically modified that. The utility function. Okay?
Sir, if you consider that there are two subsystems,
Right?
and both of them have same amount of data.
Right. So if they have both same amount of data, it's possible that you have this scaling, you remember the learning rates, there will be some difference. So you don't pick exactly same values for all of them. There's always going to be some difference. So that even though the rest of it is the same, the scaling factor or this zeta, you see that the scaling factor here, the zeta may be slightly different. So one will be accessing that network earlier than the other. Okay?
Sir, is there any priority option of subsystem?
Is there any what?
Priority option?
You can also include that. You can also include, say, let's say somebody got to like a Modi ji or someone like a VIP coming in. Well, you basically give preference, right? So if you are giving priority, you can also enter that. Yeah. But the way you enter that is through that back-off interval. That means that they don't back off longer. They basically will have access to the network much faster or the highway. You see? Got it? Okay, so here is we'll see this in the next slide. This blown up on this algorithm. So algorithm 8.1 and 2 represent the proposed optimal design. 8.1 shows the value function. So basically here is the picture. Look at that. BI stands for back off. This type of shaded one, you can see that CPS pair obtains wireless channel to transmit data. So it's accessing the channel. But if there is a collision or if somebody is already transmitting, then you back off. Then you try again transmit. So this kind of thing goes on. You see the first CPS pair, second CPS pair. So you will see that mth CPS pair. So they always have kind of a, like a shifted And you see that this type of thing means CPS pair waits while wireless channel to be free. So if you look at this guy is transmitting, so this guy and this guy has to wait. Because only one can transmit. Got it? Only one can transmit. So that's what you're adjusting. And once you adjust it, then it goes. So this basically shows that given the multiple CPS pair optimal control, select the CPS pair with highest utility. See that? Highest utility. So the highest utility, that is the lowest or the shortest backoff interval. When you have the highest utility, it is the shortest backoff. So everybody will back off, and the one that has the about to have more data will have the shortest backoff, and then he's going to transmit first. Highest priority to access the shared communication network. In addition, the proposed algorithm can render the best performance schedules for every CPS pair. So we have to show that if you have 10 of them, everybody can be transmitting and they are able to maintain. And we also have to show that the network is not always free. Because like as I said, if the highway is, because of this, your bad, our bad method, if the highway is, nobody is traveling, then it's a bad thing. We have to utilize the highway up to 99%. And we are going to see that. So let's look at the algorithm 8.1. So you can see this is mainly for the controller. So here you are estimating the h hat is equal to 0. You calculate the value function estimation error, which is the Bellman error. Then you update the parameters h hat. Then control input, calculate the control input matrix using h. Then you computing the Kalman gain for each of the systems, and you keep doing that. So you do that for all of them, and you increment the time. So algorithm 8.1 is basically for the optimal control policy. In 8.2, so here you are initializing all the wireless network control system states while you are between the slowest time to the next time. Implement the control inputs from the controller. If multiple control inputs have been received at the system on the same time, then apply the most recent control input to the system and discard all other control inputs. Now, why are we receiving multiple control inputs? Remember, we talked about the protocol, TCP/IP. It's possible that multiple of them can travel different routes, and it's possible that multiple of them would come, and you pick the most recent one based on the time, and then you transmit that and you ignore the rest of them. If old control input is received or arrived after the new control input being received, then discard the old control input and apply the new control input to the system. Else the control input is received by the plant at different time and kept in order. So basically what happens is none of them arrive, then you keep the same one that you already have from the last time instant. Then once you have received it, each subsystem receiving it based on this logic, then you apply all of them. And then once you apply, then all of them will try to access the network for transmission. And then you need to go to 8.3. So what does the 8.3 distributed cross layer? You see that it's called cross layer design, scheduling design. So here you are initializing the beta naught. And each wireless broadcasts its utility function. You see that that's the utility function. So it tries to broadcast. Everybody says that I have this priority, I have this priority. They broadcast in the network. Okay? And then everybody receives that information. And that information is a function of the value function. Look at that. The value function from the control. Then as the time, you determine the backoff interval because there are more than one that wants to transmit. And the one that has the highest utility function has the shortest backoff interval will be the one will be given to enter that network, or it will be. So you're contending the wireless source, then the smallest BI then transmits first. And then this is how you're scheduling it. Okay, then it broadcasts the message to notify all the users that once it's completed, it broadcasts the wireless channel is free, so then it goes off. You understand that? So this is how the protocol works. Once you compute the control input, and then these two keep going back and forth. Okay, any questions here, guys? Any questions here? So there is optimal policy, and you look at it here, the utility function. The utility function uses the value function here. You see that? It uses the value function. And the goal is to maximize their difference. So you want to convert, so the negative sign. So that's what you're doing. You're trying to maximize it. Any questions, guys? Any questions here? I want you to read this after today's class. And then, remember, if you don't read it, you probably will go. Tomorrow if you come, it will look very new. So how many of you are spending time every day? I see only 3 people. All the students probably are not doing it. And some of them are not coming. I think I see that names. Maybe they have other things going on. Yeah. Okay, guys. So now, still not done yet, looks like. So basically it notifies the other user. Then you see that then it updates the entire wireless network, the utility function. And then you try to balance it. Wait for the wireless channel to be free, and then you update the timestamp and also the back-off interval. And then you update again. So what happens is this keeps going on. You're updating the utility function, you're updating whether the channel is free, then again you schedule all the players, and one of them only transmits. Once it transmits and it's done, then basically it sends out a message to the network saying that I'm done, someone else can use it. Now in a highway, what happens is, let's say the car exits. As the car exits, there's another light, and it exits, it senses it and transmits to others, knowing that the car has exited the highway. Okay?
So what is the timestamp?
Timestamp is basically each of the packet has a timestamp, and also remember the network has to have the same time, global time T. Global time T, right? The network has to have some time. So this time is same as the sampling interval in the control. And they both have to do this at the same time, okay? And TS, you see that the TS is a sampling interval. K plus 1, K plus 2. K equal to K plus 1, that is basically the new one, okay? So there is also called fairness in networks. Fairness is an important factor in scheduling. So what is fairness? So imagine that you probably might have seen it. Somebody always get a priority, right? Let's say you're waiting to enter a highway. And nowadays, a lot of people, we might have seen this because, like a movie theater or a temple, you are entering a temple. How do they give priority in a temple? Huh? One is passes, but there's other way they do now. Donation or pay, like there's a ticket. You have different, if you go to Tirupati temple or something, they have a different pay. Somebody they have a general category, you don't need, only you get a ticket so that you can go. It's free. Then somebody who want to wait for 5-6 hours, they get 200 rupees or something. Somebody who really want to get, you pay 1,000 rupees or something and you get a golden ticket, whatever. So that guy doesn't stay too much. So what they do is at the entry point, they will let anybody waiting with the 1,000 rupee ticket, they'll say, oh, go. And he'll goes first, right? And the other group and the free ticket guys wait forever. So, but then there is a called fairness. This is a big deal in networks. Fairness means it's unfair. If you are entering everybody, that's what they do. But everybody entering with these tickets who are paying more, but then the guy who was poor probably would be standing there forever. Right? So how do you measure something is fair? It's not fair, right? The word fair. So there is a criteria called fair. It's called fairness index. So that means that they want to make sure that index is high for everyone or equal. You see, because somebody is getting through some, free tickets. So the way they do it is, in most temples, when you have one person or two people going with the 1,000 rupees, there's one person going at 200. Okay, and there's a zero. But then what happens is, when there's nobody in the highest paying, then you let the guys with the free tickets, they let them go fast. So there is a way that they adjust the number of people going in. Okay, so the same thing here. So we want to, in network scheduling, it's a bigger deal. We have to ensure that all the users are treated fairly. Why did this problem occur? Because a lot of them are, a lot of processors are accessing memory. A lot of users are accessing shared resource. But if you imagine, if you have a network and you are sending an email, and the email takes 4 days to reach, whereas someone else like me takes 1 day, it becomes unfair. So that fairness is a way to make sure that everybody gets through. You see? And the fairness index is a big deal in computer networks. So there you see that important factor. A fairness index is defined as, you see that RI, the weighting factor, the traffic load. So if you have more traffic, then you should be given more opportunity to access the network. You see what I'm trying to say? So if you have more traffic, you should be given opportunity to access the network. Unless you access it, you will not be able to transmit those information you want to communicate. So that's how we basically try to find a way to check the fairness index, okay? And we basically do that, and and then try to compare it, whether everybody has been treated equally or close enough, close equally, okay? So let's see whether it works. So we start with our very popular example. So this example is what? Can somebody tell me? Batch reactor, that's right. So this is a batch reactor, inherently unstable system. Got it? And so you have the batch reactor, and B is not a vector, it's a matrix, non-square matrix. So we are going to check the proposed stochastic optimal control in figures. So the page limitation, the book doesn't have all the details, but look at the papers. There's a lot of papers that have more details. So look at that. So you're able to control, basing the optimal control, the Bellman error converges, the control policy converges. We know this because we have done that, right? Now look at that. Look at the network latency. You see that there are 10. We have 10 pairs. And look at that. The traffic delay increases, then it transmits, the delay goes to 0 or comes down, and then the delay picks up again, and then it transmits again. So these are 10. 1, 2, 3, 4, 5, and so forth. So it transmits, the delay increases, then it transmits. Whenever it transmits, what will happen to the delay? It goes down. So this MATLAB code is there, and I'm positive Professor Bera would share it with you. Take a look at it. So this has the optimal controller and the scheduling algorithm combined. You can run them together. Okay? So whereas when the one that transmits, you see, as we talked about it, the one that is waiting, unscheduled wireless pairs have to wait, the wireless network latencies increase. So that's why you see that this guy is not transmitting, it's increasing. And it's given a chance here, then it transmits. The third one gets a chance here, and it transmits, while the others are waiting. And the fourth one gets a chance here, it waits, and the other one not transmitting. Now, so wireless network latencies increase based on the BI values, the back-off interval. So what we do here is the utility function. Look at that. The proposed method essentially has the maximum utility. And after some time, as the number of we compared with other methods that are very popular. One is called greedy scheduling. Greedy scheduling means the ones with the maximum one will ultimately transmit. We also have embedded round robin. Round robin is if there are 10 people, you go first, you go second. You know what I mean? So one at a time, you already assign that, and then you are transmitting. So what happens is, as the number of the network delay increases, and that causes problems. And then the other one is the greedy scheduling. Greedy also fails, whereas our approach maintains the maximum utility value. Now look at this fairness index. So what happens typically is, when one of these approaches have maximum utility and you keep transmitting, but it doesn't become fair. A lot of times it becomes unfair. So to check the fairness, we did that, and look at that. In this case, embedded round robin is very high fairness. Next, the blue, our approach is very close to the round robin. And look at the one that has a very low fairness index is the greedy scheduling. Now, why is that greedy scheduling has the lowest fairness index? Why? And why is the round robin has the highest fairness index?
In round robin, everyone is big number.
Exactly. It doesn't matter how much he has information. You don't have any higher priority. Everybody gets equal priority. So therefore, everybody is equal. That's why it is highest. In a greedy scheduling, why is it low?
Because everyone has
Doesn't get to transmit. Yeah, it doesn't matter how much you have the data. You don't, you don't transmit. So somebody is telling you, you got to wait. In the temple case, the poor guy waits for 7 hours, That's what that is. Whereas in the proposed approach, you are taking that information and you are basically using a very calculated thing. Therefore, you see that it's still high enough, like 99 something, but it's not as high as the round robin. You see that? At the same time, the performance here, you see that on this plot, we're able to show that the performance is better than the others. So that's because you're communicating between the link layer and the application layer. They're constantly chatting. You see? So this is very important. Now, why is this important? Because, remember you saw in the previous example, so if you have a protocol, you tend to wait longer. And if you don't use the proper scheduling method, this guy waits forever. This guy waits forever. And that increases the network delay and packet losses. The system will become unstable because it's running open loop. Remember that? It becomes unstable. So that's why you have to have a communication and take information from the link layer to the application layer. All of us as engineering people, we write code in the application layer. The computer science guys write in the other layers. Many times they don't talk to each other. That's the problem. Okay? You see? They don't talk to each other. Okay, so it says here a little bit, a third, the utility function with different scheduling schemes. The proposed cross-layer scheme maintains a high value of utility. And the other one, round robin and greedy, are much less than the proposed scheduling. You read that, it gives you, and eventually the fairness of different methods have been compared. The fairness indices shows that the proposed method is reasonable, compared to the others. Okay? So tomorrow, I'm going to stop here. I'm going to start 10 to take. So tomorrow we're going to look at the event triggered. So event triggered is, once you do this scheduling, I want to design a triggering mechanism to transmit those packets. That's another additional new thing that came out in 2009. That, remember I said the way you sample the closed loop system, and typically the sampling interval is what? In the previous TS is a constant. The sampling interval is a constant. But that doesn't work when you are bringing the network. So now what we're going to do is we're going to alter that, and we're going to stretch if somebody doesn't have to transmit, he can wait, we can stretch the sampling interval. Otherwise what will happen is that particular node will have more data to transmit, And even though you're doing scheduling, it may not be enough. So there is a new method called event triggering. Okay? How many of you heard that? Event triggering. So why? Did you guys, are you working on the event triggering? So who do you work with? Huh? You need to talk louder. Professor who? Huh? Oh, so he's doing event triggering. So event triggering, we're going to talk about that. Yeah. Okay? So tomorrow, again, all this is very brief. There's a lot of papers have been published in there. We're going to talk about it. So in event triggering, it's like a signal light. There's a switch. And you basically, you stretch it, you keep it in open loop. And when you're about to become unstable, then basically the switch that would give you increase you remember in our case it increases the utility. And the back of interval will be shorter and then you transmit. That's how you do it and we're going to talk about it. Okay? So we're going to talk about that in the next tomorrow, first thing tomorrow. Okay? So I want you to check this part of the code. This is chapter 9. I want you to look at this. This is chapter 9. There's no event triggering. But eventually we're going to get into event triggering. Okay? Now, I can give you a little background. Event triggering, we have 5 minutes. So I'm going to discard this. Now, if you remember, intro to NCS. Do you remember this intro to NCS? You keep going back. This is event triggering background. So you can see that here, so you have the network, you have a sensor that's willing to transmit, but then there is a switch which is controlled decided by either the time-based or event-based. Time-based is every 5 seconds, periodically. Event-based means you basically look at some performance. In this case, you're looking at it whether the system is going to become unstable. Then the one that's going to become unstable first will get the priority to transmit the data and then closes and goes out. So you sample the system states, then the decision is how frequently to sample the plan, then and how frequently you transmit. So in a classification, you have the time triggered, which is periodic. You can also do event triggered, which is based on which one goes. So in a time triggered, you see this signal is periodic. You're transmitting every periodically, which is given by TS, a fixed sampling interval. Look at the event triggered. Event triggered, this duration changes based on stability. You see that duration changes. So this duration changes. Main advantage, reduces the communication traffic and saves the network resources compared to time triggered. So that's the main reason, because you don't need to transmit a lot of packets, from the sensor. You can do that. Main drawback. What is the drawback? Inaccurate trigger condition might cause the system unstable. So if you don't decide when to switch and when to transmit, you're running in open loop, and if you are not able to transmit, your system will become unstable, because if you don't decide, that guy will get the preference. So how does it work? This is what we're going to use it. There are different ways you do that. One of them is zero order roll. So you have a trigger. You see that this is a discrete time system. X of k plus 1 is a times x of k. So you have a trigger. You compute the error, 0 volt. So current value of the state minus the previous value of the state at the previous time instant. You are comparing this time, and that is computed as the measurement error. So what you do is, your last transmitted value is xi. The current value is xk. You are measuring the error. That error keeps increasing because you are not transmitting. and if the error increases to some value and you know that's going to cause instability, then immediately you transmit. And the error becomes. How do you determine that condition? So here is the control input design in the event triggering. So is UK equal to K times XK when the event is initiated? That means the switch closes. Otherwise, you're holding that based on the previous value of the control input. Okay, previous state. So then the closed loop error, measurement error is given by this equation. Here you know A and B, you can analyze the stability of the system. So the error becomes 0 when you transmit, otherwise it does become 0 when the event is not initiated. And K is the stabilizing gain, given A and B. So people have designed this and they want to make sure that this system doesn't become unstable by designing a condition. Now, how do you design a condition? That condition is given by this equation, which is I showed you. When the event trigger error is less than or equal to this, a function of the state, okay, the event should be triggered. So if this condition is violated, then immediately the switch closes, the event trigger error becomes 0. That particular node transmits, need to transmit. So that error is tied to the distributed scheduling. Understand that? That error is tied to the distributed scheduling. How do I get this theorem? Through the Lyapunov proof. So we'll talk about that.
So this particular thing will be available in book.
There is some available in the book. If you need more details, you have to look at the event triggered control book. There's a new book that has come out last year, okay, and it also has MATLAB code. It's come out. It only talks about event triggered control. And that has come out last year, and you can look at it. In this current book, there is some information in that event triggering, and I'll cover it in the next tomorrow. But not a whole lot. Okay? Any questions, guys? Any questions here? That's why this slide deck is called intro. Remember that? It's an intro. It's not giving you everything, you know. Any questions, guys? So we are a little past 12. So I want to ask you any questions. So remember, don't forget today, what time is the afternoon session starts? 3 p.m. So be here around 3 and we'll start at 3:15. Okay? And I think don't waste your time. What I mean is that means you can enjoy. You may want to use those code that was provided, run that. Remember that? Use the time to get your homework done and all that. And today's tutorial is the third one, right? And you will have the final one on the Wednesday. Tomorrow you don't have anything. And day after tomorrow is the last one. And when is the assessment? Thursday morning is the assessment. And the Thursday afternoon you will get the grades. And okay? So I use the time, run the MATLAB code, and I already gave you the code from general pattern. He can only teach you how to do it, what to do. We won't be able to teach you how to do it. You guys have to figure it out from the code. Okay? Any final questions, guys, before we break for lunch? Right, this is only zero order whole. So I won't use first order whole. We are going to go into what we call adaptive. And we won't cover in this course. If you use the other course, event triggered control, there we'll talk about it. Yeah. Okay? Any other questions? I know if you have taken a digital control class, we talk about zero order whole, first order whole, higher order whole, the same thing, Okay? Any other questions, guys? Any other questions? Yeah.
Sir, in the control design of event trigger, whenever the event is triggered,
So the state is communicated to the controller. Then the control input is updated. You see what I'm saying? the control input is updated based on that equation u equal to kk times xk. Then that control input is transmitted to the actuator. All the three things will happen. Right. When the event is not triggered, the zero order hold maintains the same control input as that of the previous value.
So what if we do not apply any control?
Yeah, I know. You were not there on the first day I talked about it. Now, if you don't apply any input at all, remember I said two ways. One is use the previous value of that. Other one is to make the control input go to zero. I know, I mentioned this in the first day. What is the drawback if you don't apply any control input or you make the control input equal to zero? What is the drawback? What is the drawback? People don't do that. Because what will happen is if you drive the control input equal to zero, the system will run open loop and the system can become unstable. So they use the previous value of the control input under the assumption that input to state stable. Remember that's assumption I talked about, input to state stable. So that input will maintain the system at least stable till you get a new control input. So this is the difference between driving the control input to zero versus maintaining the previous control input. Got it? Okay, what else? So all this stuff has come in the last 10 years. Now it's old now. So when we do not on Thursday, on Wednesday, because Thursday there's no lecture. Wednesday I'm going to talk about future path. How many of you heard of Industry 5.0? I'm going to bring my laptop on Wednesday. So tomorrow I'm not going to play the video. So maybe I'll bring it on Wednesday and then I'll play the video. So how many of you have seen a video of Industry 4.0? How many? Well, let me rephrase it. How many of you heard of Industry 4.0? I think you guys need to. Yeah, I think I'll show you then. I think it's important because some of you don't even know. Guys, you need to get your act together right now. Don't graduate. You'll be in trouble.
So this is the assignment 3 what I have said, and this is with the nonlinear system. And can you see the structure of C matrix here? So why the C matrix is like this? Can you correlate with the discussion? Okay, let me see the that slides also, so that a little bit you can correlate the slide with the slide. Okay. So this is the slide we are talking about, optimal control of unknown nonlinear NCS using neurodynamic programming, finite and infinite horizon. Okay. So if you have this nonlinear plant in equation number 1, then you have to find out the original nonlinear plant, then the nonlinear NCS representation you have to find out. Means with the delay and packet loss, like linear system, what we did that AZK and BZK we have found out. Similarly, also you have to find out the nonlinear system representation using the network imperfections like delay and packet losses. Okay, fine. Then you see that we can do it by two ways, as Sir said. You see the ZK, which is defined using the state, and the previous inputs uk minus 1 to uk minus b, and also you can do with the that is by output of the system, that is y of k0, where the output and all the previous inputs are there, and then you have to find out the augmented system representation, which is represented by equation number 2. And here you can see, very important what I am asking you, that to see the structure of the C matrix, where you see that when C matrix is invertible, okay, so the C matrix must be invertible, the NCS model can be represented using the input output data, which is represented by equation number 3. Okay. These are the steps you need to follow, and then rest of the things like linear system, what you did, that the stochastic cost function has been defined, fine, then the stochastic cost function using input output form is also here defined in equation number 4. Okay. Then the value function, then the HGP equation. This is for the finite horizon optimal control. This discussion already it has been made. Just I am showing you such that you can once again you can recollect it. That what we are going to be talking about. So this is the critique NN weight update, the actor design, and corresponding NN update law, and this is the flowchart ultimately for finite horizon stochastic optimal control. So here at least you will have the idea of overall control system. So here basically in slide it has been given for a folding manipulator system, but in your assignment for a lower dimension of system it has been given, and corresponding the MATLAB code is also provided. So that you need to see that how it is performing for different cases. So what is your that is figure 6.7? That is the state regulation errors by using NN feedback linearizing controller with network imperfections. So in this case you are finding that error are growing. Okay, so that is also there in case of that particular system which is given in the assignment. Okay. So that you do first, just to run that one, okay, and you see that what are the plots are coming, and then you see that what are the inbuilt functions are, means that subroutines are defined there, and try to understand at least with the block diagram or the flow chart, the things are going accordingly or not. That's all. This much only you do, that is more than enough. Then when you will get time, you will, more details you will look into the problem. Only two problems are there. Huh?
The code model is taking is for the problem number 1.
Yes, yes. You will find that not for the robotic manipulator, it is for this system only. Okay, for this system only. One is for finite horizon, another for infinite horizon. Same system, one is for finite, first problem is the finite horizon optimal control, and this problem 2 is for your infinite horizon optimal control. But the system is kept same. So you just see that particular programming and you see that how it is working.
The dimensions should not be a problem. Because if you look at tuning robot, it's very similar dimension, so there shouldn't be any change in the dimension.
Yes, but here the B matrix dimension is different from the robot dynamics.
Because there it's a 2 by 2, here it's 1 by 1.
So then actually lot of changes they have to do. I saw. And in programming, if it is the single input case, then it is much simpler. But if it is a BMOS, means at least multi-input is there, then need to be changed rigorously. Because many steps are there where you need to change for the different dimension. Little bit involved work is there, they have to do for the change in dimension.
That's why they have to understand the code, what it's doing, then only you can make that change. Unless you do the change, you won't get that, how to write the MATLAB. Yeah. I don't know, have you guys, any of you have written this much MATLAB code? Huh? You have written, but no other, see, I think in real life, he works for industry. You got to write. That's what I'm saying, that's a realistic example. So he works for industry. Yeah.
So this programming, you try to understand that for actor, what is the error, for critique, what is the error, and how these errors are calculated here. At least this much you understand. Today morning only sir told that what is the error for the critic, what is the error is utilized for the actor. So whether that errors you can identify in the programming or not. That errors are calculated, you see.
No, even though the G is, matrix is different, it shouldn't affect here.
Okay, they can try.
You know why? You know why? Why is that G dimension shouldn't be a major issue?
G is related to input U.
It's input U and G is usually in the input U. How does the G appear? How does the G appear? You remember half R inverse G transpose. So rather than, you don't have to take the inverse of G and all. So G transpose for for a vector is pretty straightforward. You remember that. So that's why. It shouldn't make it very difficult. The only thing is when you are even in the system dynamics, it shouldn't be that hard. Remember the system dynamics, you have to get the new state vector. You have to call the routine and you need to get the state vector, right? So there also should be. So it should be very difficult.
Now some steps are there, they are actually for plotting or these things, their calculation is there. That's for that calculation, they need to change the dimension. Otherwise, as you say. Sir, if you once again, if you tell that why in this case the proposed one we have in the middle, the cost, but in case of NN-based feedback linearization, why the cost is higher?
So okay, let me ask you this question to you. I did mention that, but let me ask you why in the case of feedback linearization, the cost is higher. You understand what feedback linearization, right? So if you have x of k plus 1 equal to f of x of k plus g times u, you are taking the u equal to 1 over g minus f plus v, right? That's the feedback linearization. So what is feedback linearization? You are trying to cancel the nonlinearities through feedback. Now it's different from Jacobian linearization. What is Jacobian linearization? Point and then you expand, right? That's how you get the A and B matrices. But this one is feedback linearization, so you're still doing cancelling it and then you still get a linear system. That's how you do it. So feedback linearization doesn't have any optimality. There's no optimality, number one. Number two, you need to know precisely the dynamics. So feedback linearization is a controller which is non-optimal. Okay? So as a result, the cost is higher because you have a gain within that. Once you get a linear system, you have to use a linear control, and you can pick your controller gain whatever you want, right? You know? Yeah. Okay. That's right. That's right. So that's one thing. Now, if you look at why neural network NDV-based optimal offline optimal controller is always lowest. Why is it lowest? This also I said. That is correct. So remember we talked about this. So when you are finding that function, you are holding the time, like it's not practical, but that's how you do it in numerical analysis or in finite element. You hold the time and then you are doing it more number of iterations. So what it does by doing iterations, you are really driving the error close to zero at every point in time, you see. So since you are doing that, but that's how the numerical methods work, right? So you keep constantly iterating it and you are driving it. So at each and every point, the value function, which is a solution to the SJV equation, would be optimal because you are driving it till it reaches a. Whereas in the proposed approach, you're only doing once. Today morning I talked about hybrid, remember that? Hybrid basically does a few iterations. You see? So it's a little better than this, the proposed approach, because here you're doing a few iterations, not a whole lot. But whereas in the offline, you basically can do, assuming that you can do as many iterations as you want, till it converges. Since you're doing it at every instant of time, V hat becomes V star. And therefore that's the best solution you can get. That's why it is the lowest. You see? So V hat will become V star at every, and therefore U hat will become U star because you're using partial V star over partial. Remember that in the control input calculation. That's exactly why. You see? So that's why you have 3 quarks. They're different, yeah. Okay? Alright. I think that's good that she's learned to at least 1. And there are 3. So at least I'm happy. And you should get the similar result. When you change the system, you should get, unless you really tune that feedback linearization gain, and you try to lower it. You know what I mean? Yeah.
So for the next problem, the infinite horizon, you will find that this is the, in slide, the system is already given, okay, the same system we are taking, this system. And here you can find out f and g, how it is calculated. The after introducing the delay and packet losses and the parameters what it is selected, it is in the slide, and this results are, because in slide when you will run MATLAB program only you can see the figures, but what is that figure, what is the analysis, that you can do it from the slide here. So you see that it has been shown that what is the drawback of heuristic dynamic programming, that is value iteration algorithm. So if you do not take the enough number of iterations, then it may diverge. Okay. Then the effects of delay and packet losses, that is shown that that error may diverge, but in case of the proposed controller, you will find that the regulation error is converging. Okay. So with this analysis, you just compare the result what you are going to get by running the MATLAB program. Okay. And this is a summary you can use to understand that particular programming. Okay, so I'm closing here, but you just see the things, okay?